so that people can talk freely and we can interact without having to worry about everything being transcribed. Yeah, and real pleasure to have Aaron presenting for us today. For those of you who are joining who aren't regulars to this group, Aaron is a longtime DFTer, did his PhD at the University of Iowa, working with me, has built a stellar career. And although I listed you as associate professor at Tennessee, I know you've been promoted to full. I just didn't know if it was official yet. So
yeah,
full professor.
Fall will be starting as full. So
yeah, perfect.
and I just got the mid-career research award from the College of Arts and Sciences here. So
Yeah,
they just told me this morning.
Excellent. We'll definitely celebrate.
Yes.
All right, so real pleasure to have you today, and I'll turn it over to you.
All right. Can you see my slides? We good?
Yes. Yeah.
All right. So I'm following up on John's presentation from last month outlining Wolves 2.0 and sort of integrating word learning processes with executive function. And so I'm going to talk about further driving the field of executive function development forward via theory, data, dialogue. An alternative title could be from executive function to label learning to executive function and back again. So John's talk last month focused on the nature of executive functions and how we can trace its developmental roots. And so within the Wolves architecture, then we can think about how early visual cognition, visual exploration gives rise to object representation processes and eventually word learning, which then lays the foundation for later developing executive function. And sort of to get to this point, it's a process that's unfolded for basically about 20 years. Even back when I was an undergrad, when I started my research career, I was interested in understanding what the DCCS task could tell us about executive function development. And one of the first ideas that I had when I was writing my comprehensive exams during grad school was to examine how dimensional label learning impacted executive function development. And so through the intervening years of empirical work, theory development, we're able to now kind of talk about this in really concrete terms. And so what I'm going to talk about today then, well, maybe reiterate a little bit about what John talked about last month, is to try to tell a coherent story where this progress sort of feels inevitable and the next steps are obvious. But in a way, it feels a little simple, but it's actually way more complex than what we would have had otherwise without DFT sort of coming into this area of research. So over the course of developing the model, we've explained a wide range of both behavioral and neural data. And really a model is only so good as the constraints that it's able to satisfy. And so all these data points sort of reflect that constraints on what the model can do and what the mechanisms and dynamics are that model displays. And what John sort of highlighted was that the key thing about the DCCS task that we've learned by applying this model is that the details of what goes where matters. So how visual features are bound to spatial locations and how those memory traces can either cooperate or conflict with task inputs across dimensions can make switching in this task easy or difficult. In other work that I'll talk about, we've also shown how dimensional label representation system can show signatures of frontal cortex activity that's related to developmental changes or changes to competition and cooperation across dimensions. And so in this way, the model also explains how the frontal cortex activity is related to performance on that DCCS task. And so we're going to consider, does the model still sort of fit with what we've talked about in the context of this task previously? And what are the sort of key elements that we need to make sure that we carry forward with us in the next wave of modeling work? But of course, as models evolve, they get more complex. It can be more challenging to sort of keep everything within that same framework. So this is sort of a broad overview of the three main things that I'll address over the course of this talk. First, and I'll probably spend the most time on a discussion of whether we're missing anything in the current state of the model and what those critical things might be. Next, I'll talk about what are the nature of dimensional label representations and how can those potentially arise in wolves in an autonomous way. And then I'll finish with a discussion of the empirical evidence that links dimensional label learning to executive function. We could talk a lot about this in the context of sort of theoretical work. And so it's important to consider also what those empirical connections are. And given that context, then what is the sort of theory data dialogue for the future? So first, yeah, what are we missing from the current state of the model? And what do we need to make sure we carry forward? So aside from all of the behavioral data that John had gone over last month in relation to processing in the model, one of the other major advancements of DFT is that it's able to integrate behavioral and neural processes. And I would argue this is really one of the bigger impacts of dynamic field theory, that it can take a robust quantitative approach to not only simulating the details of behavior, but also simulating associated brain responses associated with that behavior. And so just like the model generates real-time behavior, the model also generates real-time corresponding neural responses. And if you ask anybody which part of the brain is responsible for executive function, even if they don't know anything about executive function, they're going to say frontal cortex, which has obviously, but for a long time, been implicated in executive function. And so developmental work started looking at frontal cortex activation in response to task demands during the DCCS. And one of the first examinations of this was in this paper by Moriguchi and Hiraki, where they recorded functional data using functional near-infrared spectroscopy from lateral frontal cortex while children performed the DCCS task. And so what you see here on the left then are plots of changes in blood flow during the pre-switch phase on the left and during the post-switch phase on the right. And the key thing here is that children that switch rules in the DCCS task show greater activity in frontal cortex compared to children that fail to switch rules. So 5-year-olds, 3-year-olds that pass, plotted in the blue and red lines during both the pre-switch and the post-switch phase, show greater activity than children that failed to switch rules. And in the context of this study, the interpretation relied largely on sort of maturational mechanisms, maturational processes, with the story being something that, frontal cortex matures, it unlocks these new skills that children are able to use in the service of behavior. And so frontal cortex is sort of causing the ability to be flexible in the context of this task. And so children that show greater frontal cortex activity are going to be able to switch rules. Somewhat of a circular argument, but notwithstanding, that's sort of the story, right? Brain matures, gets increased in activity, and creates these skills for children to use in the service of behavior. And so from our perspective, this sort of begs the question of what's happening neurally in the DCCS task when young children are able to succeed on these easier versions of the task. And one of the conditions that John had gone over last month was this no conflict standard version, in which even young children are able to successfully switch rules. And so just to remind you of sort of what we're talking about here, we've got our model with fields responsive to color or shape information with these little hotspots corresponding to memory traces or task inputs for features at spatial locations. So this would be, for example, blue on the left, red on the right, and circle on the left, and star on the right. Now, the key thing about this particular condition that makes switching easy is the fact that children sort cards that match the target cards along both dimensions. So they're seeing a blue circle on the left and a star on the right, and they're told during the pre-switch phase, for example, to sort by color, put the blue ones over here and the red ones over here. And then children are given a blue circle and a red star to sort. As a consequence of sorting these no conflict cards, children lay down memory traces that are essentially supportive of what they'll need to do with those features during the post-switch phase. So they have memory traces not just about blue and red going to the left and right, but also circle going to the left and star going to the right. So now when children are told to switch and sort by shape, put the circles on the left and the stars to the right, they now have standard sort of cards that contain visual conflict. But they have these memory traces that they're able to carry forward. And so this is sort of illustrated over here by this sort of cooperation. This is kind of just a cartoon diagram to illustrate these things, right? But the little red hot spots on top of the inputs show that there are memory traces that correspond with the inputs in both the pre-switch, but more importantly, also in the post-switch field. And so in this configuration of stimuli, what kind of consequences does this have on brain activity? And as our initial sort of foray into this, brain-based simulations, our assumption was that frontal cortex would correspond to the label representation system. And just to recap, this label representation system is implemented as discrete nodes for a label for shape and a label for color that have reciprocal connectivity with their associated neural populations, right? So activation for neurons encoding colors and spatial locations would interact with our color label representation, and neurons encoding shape spatial representations would interact with our shape label neuron. And so when we administered this model to the task and we simulated blood flow responses from different components of the model, we found this interesting prediction illustrated by the simulated data over here on the left. We have our young model that has weak coupling between labels and visual features, and our old model that has stronger coupling between labels and visual features. And then brain activity during the standard condition is in the solid line. The no conflict condition is in the dashed line. And first, I'll just highlight the fact that the model replicates that Moriguchi and Hiraki finding. The young model that fails to switch in the standard version shows little activity in frontal cortex when failing to switch. The older model that is able to switch rules shows a much stronger neural response. But most importantly, what we're seeing here is also this little blip here. There's an increase in frontal cortex activity in that no conflict condition, which arises through this reciprocal connectivity between object representations and labels. So when we have this confluence of memory traces and inputs in this post-switch field, it's creating a stronger bottom-up signal that essentially kicks the frontal cortex system of the model into gear and creates a stronger blood flow response on the dimensional labels from this model. Now, when we ran this with 3 and 4-year-olds, it took a bit of ingenuity. Typically, when you do the DCCS task, children just come in, they do 5 pre-switch trials and 5 post-switch trials. And that's not nearly enough data to analyze associated neural responses. And so we had to build this sort of interleaved switching condition where children did lots of different switches in order to get enough neural data from this particular task. But when we did that, we found remarkably that the brains of 3 and 4-year-olds supported the predictions made by the model. So again, just working through this systematically, right? The solid line here, children that failed to switch in that standard condition showed weak frontal cortex when they failed to switch, but those same children showed a increase in blood flow in frontal cortex in this easier condition, right? Suggesting that frontal cortex activity is not just about maturational status of this brain region. It's more about perhaps how it's connected up to other processes that are unfolding in the brain and is more open to these influences from perhaps posterior object representation areas. And I'll come back to this as one of the critical elements that I think is important for reflecting how this neural architecture is sort of dynamically operating as we think about how to train up executive functions and what the next steps might be to test predictions of the model. And so between everything that we've simulated prior to this and the brain-based responses, there's going to be lots of different steps, right? So what we've done with Wolves 2.0 is to show that label learning and executive function processes can live in the same domain, right? That we can manipulate these learning processes as it relates to comprehension and production of labels and get associated gains in executive function. But are we still able to capture all of those different things that we've done with the model before? Which of those are going to be the most important as sort of assessing the status of this model as we go forward? And obviously working with, an autonomous model with more components is going to be difficult. And so we just need to have a clear sense of what we need to take forward from our previous work to assess that status of the model. And so as just an initial survey, I threw a bunch of different conditions that we had done before at the model just to sort of see, are we getting things right still? It doesn't really make sense to look at the neural responses yet until we sort of get these behavioral effects nailed down. But so, for example, there's a condition, the negative priming version. Oh, Am I
Yep,
am I
you're
still
still
on?
good.
Can you guys hear me?
Yeah. Yep. Can you hear us?
Yeah, we still hear you.
Hello?
Yep. All good.
Maybe you don't hear us. Is that the
Yeah.
problem?
Oh, am I back now?
Yeah,
We
you were
hear
there the
you.
whole time.
Maybe you don't hear us.
I didn't hear
You
you.
hear
I had a
us?
screen that said, "Hold on, something went wrong."
Okay. Okay. Yeah,
I
you're
can hear.
good.
Okay.
Okay, good.
Yeah, so we threw a bunch of different conditions at the model that we had done before. So first, this negative priming version. And in all of these examples, color is the pre-switch dimension, just to anchor this to something consistent. So the features that children sort by during the initial sorting phase are changed when they're instructed to switch. So if they sort by color, they're then told to sort by shape, but the colors have changed. In this case, young children still fail to switch rules, but that doesn't appear to be the case in Wolves 2.0, looking at the passing rate, the failing rate, and then also the mixed performance rate. Switching is still difficult in this version because of this competition that's maintained for this post-switch dimension. So they're sorting a star to the left during the pre-switch phase, and now in the post-switch phase, they need to sort a star to the right, right? They sorted a circle to the left during the pre-switch phase, and now they need to sort they sorted a star to the left, they need to put it to the right, they sorted a circle to the right, and they need to put it to the left. That's that competition here, which in the previous model, the model failed like 3-year-olds. In the no conflict condition, which would be the next one here, this is the one I just went over, was the basis for that brain behavior prediction. 3-year-olds, young children, succeed in this version, not so much in Wolves 2.0. In the total change version, everything changes between the pre and the post switch phase. The model's doing a pretty good job here with still a high rate of mixed performance. The more autonomous label representations, I think, sort of creates a little less all or none performance. Typically, children's performance in this task is they either get them all right or they get them all wrong. And so when we see this higher rate of mixed performance, that means sometimes they're sorting correctly and sometimes it's not. And then the last condition that I looked at was the no conflict negative priming. It's sort of a combination of the no conflict version with that negative priming change in features. 3-year-olds are successful in this condition, and the models may be a little bit too successful in this condition. And so across these different manipulations, we can see what's happening in this post-switch field isn't really driving performance in as robust of a way as it was in the previous version of the model. This competition should make switching difficult, and that's not really holding up. This cooperation here should make switching easier, but that's also not really holding up. And then we need to sort of address this the robustness of the all or none performance of the model as we further iterate and refine perhaps the tuning of the model, right? So it could be about the balance of that spatial coupling and scene working memory, how strongly visual features are projecting into the spatial response selection system. But I think it's also important to point out that Wolves 2.0 really has sort of a different model architecture. There's different dynamics that are happening between the object representation system and the label representation system. And in the previous model, labels were strictly competitive, right? If a shape label is active, that's directly inhibiting the color label. In Wolves 2.0, however, there is an active binding process, right? Features are bound to labels, which is an essential element of how labels are learned in that architecture. And in the previous model, the associations between labels and populations in the visual dimensions was Hebbian, right? They were connecting up via Hebbian connection weights. In Wolves 2.0, however, these associations are memory trace based, right? So they're building up within a dynamical population that actively binds labels to visual features. And so it's maybe not so obvious that we would have these same effects living across these different architectures. To illustrate perhaps a challenge with thinking about labels from a Hebbian, from a memory trace perspective, this is a snapshot from the model. I just pulled out the essential components of that much larger architecture that John was presenting last month. And so here we've got our object representation system for color and shape and our spatial response system here. This is our corresponding populations for mapping labels to visual features.
Hey, Aaron,
Yeah.
are you able to use your mouse to point?
Do you not see my mouse? I'm making gestures,
Yeah.
but
I thought you were
is it
making
not?
gestures because Yeah, it's not showing up. If you
Let
click
me
down
see
in
here. Is there?
PowerPoint, in the little
Nope.
icon at the
Oh,
bottom of the PowerPoint slide.
yeah.
Yeah,
Let me see. Laser pointer.
there we
Is that
go.
working? Okay.
Yeah, thank
So
you.
this is our object representation system here that binds colors to space and shapes to space. This is our spatial field that serves as the basis for making a left-right response. This is our label learning system here. So our label representations up at the top that are binding these actively to either color or shape features. You can kind of see here the Hebbian traces that we implemented to reflect that learning process. And so this would be very early in the process after the process of decision making after a stimulus has been presented. We can see that label being bound to, in this case, the color, and the model's being told to play the color game. And early on, there is an advantage for that color label to bias activation of this particular feature in object representation system. But before that object binding has fully resolved, we can see here there's a peak binding for this color at the left location. That's still emerging in the shape population down here. It hasn't quite fully bound. The spatial decision is emerging up here, but the model has activated label bindings for that label to both the color and the shape feature. So now that competitive advantage for this feature sort of goes away pretty rapidly as that label binding process unfolds. And so this label binding is essential for how labels are learned, right? We need to be able to potentially associate a label with any particular visual feature until we fully resolve what that means. But I think there's a distinction then between sort of learning a label versus using a label. And in the sense we want to use a label to bias attention towards things that are task relevant, this binding can sort of muck up the clarity of what's being attended to based on the activation of a particular label. As an alternative, we could also perhaps use a Hebbian connection matrix rather than neural populations that do active binding to connect, for example, our label representations to a label feature population. So this would be a color-sensitive population whose activation is driven by the connections associating a word with that feature in a Hebbian matrix sort of sense. So we take this activation of this label, project it through this weight matrix. It overlaps with strong weights here, which then projects out to this particular location in the feature field. And just sort of playing with this in a very cursory way, we can see that we can get sort of selectivity in terms of what's being activated or attended to, because this label doesn't have strong associations with the visual feature in the shape population. It's not getting a strong boost to that shape feature in this population, but it is getting a strong boost to that feature here in this population. So now we can perhaps recover that selectivity of activating a label and setting some attentional template that could still work within this sense of learning these labels in a flexible way. And this whole process of going back and forth here reminded me of one of the points that Gregor makes early on in his sort of introductory DFT lectures, sort of highlighting the advantages of binding via two-dimensional dynamic fields, right? It's fast and flexible form of association that contrasts with that slower form of associative learning that's traditional in connectionist networks. But here we can see sort of a more practical sense where certain sort of mechanisms might be more well suited for some jobs versus others. So as we explore and expand on this model, we can sort of actively compare the Hebbian picture to the memory trace picture to see are both of them able to learn labels equally well? Are they able to guide attention equally well? Perhaps there still is a role for binding labels in an active dynamic way. Maybe that couples up to our object representation system or not. And so there's flexibility in terms of the types of architectures we can explore going forward to see how to get these dynamics right, to be able to address label learning and how sort of cross-situational label learning has been explored in the model, but also now venturing into dimensional label learning and attention-based sort of effects across measures of executive function. So are we missing anything in the current state of the model? I've highlighted a couple things that we need to work on. I think perhaps all of those behavioral effects aren't going to be as critical as we go forward, but I think essentially we need to get that brain behavior effect to live in the space of this model. And as I get to later on in the talk, I think that's critical because it provides a way to think about how learning can create changes in brain function in a way that is impacting executive function development. So I'll turn now to looking at the nature of dimensional label learning. What do we actually know about it? And how might this sort of learning process arise in wolves or future iterations of wolves? And we know a fair bit about sort of the behavior associated with the comprehension and production of dimensional labels. But we can think a bit about sort of what the learning problem is that a learner faces when trying to acquire dimensional label representations. And labels for features, things like the word red or the word square, are things that could probably be learned relatively easily just through cross-situational statistics, right? As you hear these labels, those will be associated in a reliable way with certain locations within our neural populations encoding these visual features. But when we think about labels like shape or color, labels for an entire perceptual dimension, those are going to be much more difficult to learn cross-situationally. There's not going to be signals in typical experience that could be used to anchor these labels to aspects of our perception of the visual world. You could imagine ways to emphasize, if you show like, two objects that have the same color and different shapes, and you just give the label color, and then do that over multiple iterations with maybe highlighting sameness along a particular perceptual dimension. Perhaps you can get there through some sort of cross-situational learning like that. But that's going to be sort of highly precise and highly, you can't really expect that type of experience would be available to children as they're learning these dimensional labels. And so perhaps there just needs to be a different kind of mechanism involved in the learning of these particular labels. And what we know about label comprehension production in early childhood is that even in the earliest stages of dimensional label learning, children are able to provide appropriate responses to production questions, right? Even if it's not the correct label. So if you ask a young child, what color is this? They're not going to say something like banana, or they're not going to say something like a verb, right? They know that color is associated with some subset of other words. And so when they're queried with a question like this, there's only certain words that are candidates for a response to that question, even if they don't know exactly the label for a particular color. And so children show this sort of pattern of performance where they get good at comprehension first. Obviously, through that cross-situational learning, they're able to leverage that acquisition of those labels. They're able to show evidence of this label associative learning process, knowing that the word color is associated with certain other labels. And then eventually they're able to bring that together to produce correct responses to questions like what color is this or what shape is this? And so in further expansions of this wolves architecture, we could take our lead from models such as Word2Vec, where the strength of associations between words is learned in that sort of a network, which could then serve as input to our word fields in Wolves 2.0, such that a label like color then could have associations that are formed with specific feature labels that are then providing the input to our label field in Wolves, as John sort of articulated that last month. And so that could be a way then to take perhaps a corpus of language input, provide it to the model, give the model opportunities to view objects, and perhaps have some autonomous learning process take hold at both levels of learning that appear to be necessary for dimensional label learning, right? Word-word association formation, as well as word feature association formation. And so in the case of dimensional label learning, it's more than just cross-situational associations between labels and visual features. There's also associations between labels. And so we can think about how to formalize that in order to give us the ability to simulate dimensional label learning in an autonomous fashion. And then the last bit of stuff that I'll talk about then is what is the empirical evidence linking dimensional label learning to executive function? So this is all good in terms of a theoretical exercise that the model is able to show these associations, that it's able to get past this sort of maturational view of executive function development to try to ground it in children's learning and experiences. And so what is the actual empirical evidence supporting this sort of perspective? And so I'll talk about data from two different projects where we used near-infrared spectroscopy to measure brain activity in early childhood at 2.5 years of age, and then to test children on different executive function tasks at either 3.5 or 4.5 years of age. And so in one study, we measured comprehension and production of dimensional labels at 2.5 years of age. We then followed up with children at 3.5 years of age and asked whether measures during this task at 2.5 predicted DCCS performance or flanker performance at 3.5 years of age. If performance on the DCCS task is really about these dimensional label representations that are being learned, then we should see that these measures predict DCCS performance, but not flanker performance. Flanker performance is more about sort of spatial selective attention and perhaps involves different sorts of developmental mechanisms. In a second study, we asked a related but sort of inverse question. We measured, again, dimensional label representations at 2.5 years of age, but we also measured performance on what could be characterized as like an early executive function task. And in this case, it was a Simon task. And the Simon task is a response selection task. Similar to the DCCS, children need to make a left-right response to a stimulus. But in this case, the stimulus response on the screen could conflict with the button press that needs to be made. So children need to selectively attend to the identity of the stimulus, ignore the spatial location of the stimulus, in order to perform well on those trials that have conflict. And to make this sort of amenable to the performance levels of a 2.5-year-old, we had it be sort of a feed the animal task, right? So it was a picture of a dog or a picture of a cat, and children were told that one button gives cat food, and one button gives dog food. So if you see a cat, make sure to give it cat food, but if you see a dog, make sure to give it dog food. And so they were making left-right button presses, while the stimulus could either be at a location congruent with the side of that button press, incongruent with the side of that button press, or in the middle of the screen. And then we asked which of these is a better predictor of performance on the DCCS task now at 4.5 years of age. We planned to collect data at 3.5, but that was during COVID, so we had to wait until in-person research could resume, and then we followed them up at 4.5 years of age. So we could think about different hypotheses here in the context of the second study, right? If it's just about maturation of executive function, then one might expect that measures of early executive function would be a better predictor of later executive function. But if this is really about these dimensional label learning processes, as DFT would suggest, then dimensional label learning at 2.5 years should be a better predictor of executive function at 4.5 years. I'll cut to the sort of key findings here, but it turns out that activation during dimensional label production in left frontal cortex is what's really important. So across both studies, we found in the first case that dimensional label learning predicted DCCS, but did not predict flanker performance. And in the second study, dimensional label learning, but not the Simon task, predicted DCCS performance later on in development. And so this is that sort of correlation. Importantly, it's about dimensional label production activity at 2.5 years that predicts performance on the DCCS task at 3.5 or at 4.5 years. And so in both cases, what we found is that the more strongly children activated this brain region at 2.5 years of age, the better they did on the DCCS task at 3.5 or at 4.5 years of age, suggesting that these label learning processes are providing a way of training up these networks of frontal cortex that eventually get used in the service of executive function later on in development. And I would say that this begs the question of how general object category learning is related to these findings, and I'll just say to stay tuned. We've got more longitudinal data coming that's comparing dimensional labels, object category labels, and how all of that fits into these pictures longitudinally. And so I think we've got sort of the perfect storm brewing here, so unprecedented opportunities where we can explore how the model learns labels, dimensional labels autonomously. If we can expand these architectures to do this in a way that maintains consistency with those critical findings related to the DCCS that we were able to capture earlier, then we would have this simulation playground where we can systematically manipulate the properties of experiences that the model gets with labels, with objects, to form label feature associations, label associations, We can simulate hemodynamic responses from different components of the model. And it's not just about acquiring these labels, right? All of these children are going to acquire these labels. It's more about how the properties of the qualities of children's experiences are optimizing engagement of frontal cortex in the context of this learning problem. And so we can take the model, run whatever sort of interventions we think might be interesting or impactful, and simulate all of that ahead of time before we take it to actual kids in the real world to see if it actually matters to their executive function development. And so we can see whether these experiences can be optimized, how they can be optimized to engage frontal cortex during label production. And if we can give those experience regimens to children at 2.5 or earlier, are we going to see a more rapid improvement in executive function as they develop? Okay, so I'll just sort of summarize with some sort of bigger picture sort of things here. And I'll return to a point from John's talk last month that executive function is typically framed around components such as inhibition, working memory, switching, attention. And so an obvious question is whether such components exist in a complex neural architecture like this. And what I might suggest is rather to take a different point of view. These cognitive mechanisms are really just descriptions for patterns of behavior. And these are useful for making inferences or predictions, but they're not really explanatory in and of themselves. And so these patterns of behavior we can think of as being emergent from these neural population dynamics within these complex architectures. Right? So practically speaking, all we can do is ask, does the model replicate behavior? Does the model replicate whatever empirical observations we want to anchor it to? And if so, then those cognitive mechanisms can be applied to the model's performance just like it can be applied to our measures from humans. But now we don't have to rely on those cognitive mechanisms to do the explanatory heavy lifting. We can let the model do the talking, and in a way that connects with our empirical observations, things that we're able to manipulate in a more direct way without having all of that conceptual baggage in between. And so what we're doing there, I think, is building a theory in the language of the brain and formulating it at a level that can produce both behavioral and neural responses with high fidelity. We can robustly constrain the models to yield increasingly accurate representations of what we think the brain is doing, to yield increasingly accurate predictions. That's the hope, right? And so I think what we're doing in the context of DFT is this process of explaining some existing data, exploring the dynamics, performance, neural measures of the model to make some new predictions. If those predictions work, great. I think it's even more interesting when those predictions don't work, because now we can go back to the model and engage in a true process of discovery to see what about the model was causing it to not replicate behavior. How can we enrich the model, further develop the model to get to a more perfect representation of how things are actually working? And as long as we can keep sort of building increasingly complex architectures, we can get away from just sort of special purpose models to more general purpose models that can generalize across tasks, across domains, and across development. And to the extent that works, I think we're actually discovering those principles by which the brain functions and how the brain gives rise to cognitive function. Thank you for your attention. That's all I got.
Wonderful.
Great. Thank you, Aaron. I'm going to go ahead and stop the recording, and then we can